We have learnt about Kiger-Marsden experiment done by Rutherford. Now, in that we have observed certain features on the basis of which few results were calculated. So, we will study one thing, that is distance of closest approach. Suppose this is the nucleus of gold located at one place and all place around it is an empty place. These are the alpha particles, various alpha particles going on this path. The one which is going on this path, this is experiencing plus, this is also plus. What is alpha particle? Alpha particle has got two positive charges and its mass is equal to 4 units. 4 compared to hydrogen. Okay. Now, when it goes from here, the positive charges are getting repulsion force from this, that is Coulomb's force of repulsion. Because of that, it experiences a force. Now, till it is coming closer to it, the force goes on increasing, because we know the formula, force is proportionate to 1 upon r square. If r is decreasing, the force will go on increasing, and you see this is the line from where it is supposed to pass. When it will become so close to it, the force will be very large force. But that situation doesn't come, because before that, when it is at this distance, when it is at say this distance, the force becomes so large that it starts deviating. Push. This cannot push this. These plus 2 and this plus 79. There is a interaction between the two, repulsion. It applies force on this. This applies force on this. This does not move because its mass is very large, but this moves. And when this moves, what happens? This will turn and go like this. This is what happens exactly. Okay, because the force was very large. Same thing happens to this, reflected. Now this second one, see this one. This distance is a large distance, so the force is slightly less. And if the force is less, then the deflection will also be less, and this goes like this. What will happen to this? This is far away, no force act on it, so it goes straight. Similarly, this one in this direction, and this goes straight. You see, the closer it is, more is the force and more is the angle of deviation. This is what happens in it. Now, there is this distance which is affecting it. If it is going to make an impact with this is the distance. This distance is called parameter of impact or impact parameter. From this point to this point. What is this? Center of the alpha particles path. And what is this? Center of the nucleus. Now, this distance between the two, this is called impact parameter. Less is the impact parameter, more is the effect of impact, and it will get deviated. Okay. Now, this is impact parameter for this particular particle. For this particular particle, this is the impact parameter. For this particle, this is the impact parameter. So, this is the definition of impact parameter. What is that? We can write it, definition of impact parameter. Impact parameter is perpendicular distance between direction of the approaching alpha particle and center of the nucleus. Okay. The effect of impact parameter we have discussed. Now we come to this particular one, which is going in the direction of center, almost to the center. What happens to it? We see that it takes a complete about turn this way and return back. How much it has turned? It has turned by say 360 degrees. Or from this direction it has turned by 90 and 90, 180. From its own direction, no, from this direction it has turned by 90 and 90, so we will call it has turned by 180 degree. Why it has turned? Answer, because there is a positive charge on it, there is a force of repulsion in it. Because of this force there is a deceleration. Because of that speed goes on decreasing. At one point the speed becomes 0. Still this force is acting, and because of that force it returned back. As simple as that. It need not to come here and strike, because even before coming its velocity has become 0 due to this force of repulsion. Now it has returned from this place and gone. It has not done a strike, and this distance, this is a very important distance, and we call it distance of closest approach, and let's give it a symbol d. So d is the distance of closest approach. Now I will write what is the distance of closest approach. The distance of closest approach is the minimum distance between alpha particle and center of nucleus just before it reflects back. Reflects back by 180 degree. That is, retrace its path. This is the distance of closest approach. Now this distance give us a certain idea. What is that idea? That is idea of the size of nucleus. D gives idea of the size of nucleus. How? This nucleus, can it be larger than D, or should it be smaller than D? Obvious, it has to be smaller than D. Now if I find out the value of D, it may be 10 to the power minus 10, minus 12, minus 14, minus 18. If I say this D is 10 to the power minus 18, that means its size should be less than that, because it is returning without touching it. So it has to be less than that. If I say this is 10 to the power minus 10, then its size is less than 10 to the power minus 10, and 10 to the power minus 10 and 10 to the power minus 18, there is a difference of 100 million, 1000 million. So this gives us a very important conclusion about size of this nucleus, because so he was in the dark as what should be the size. The size of atom was calculated, and that was 10 to the power minus 10. Now this must be smaller than 10 to the power minus 10. Can it be 10 to the power minus 11, minus 12, minus 14, minus 16, minus 18? How small? That was a big question, and that question was solved by calculating this D. See how it was calculated and how we could find out that what should be the size of this. So, what was the utility of distance of closest approach? Answer, it helped to find out the approximate size or the limit of size of the nucleus, that how small it can be. Because what was the principle? The size of nucleus should always be less than distance of closest approach. Because if the size is so big, this, then this cannot cross this. This will go and come back from here. This will not enter here. So, this size has to be less than this if it comes from here. But if it comes from here, then it means this size is only this much and not this much. So, that D gives the idea of the size of nucleus. And now we will see how it is calculated. For calculation, from here alpha particle is going and it is having certain velocity, and because of that velocity it has got kinetic energy. Now on this path here, because of the continuous force of repulsion, here its velocity becomes 0, the kinetic energy becomes 0. Where it has gone? Answer, it is converted into potential energy. And then when it returns back, that potential energy is again converting to kinetic energy, and the speed goes on increasing, and on a path, kinetic energy and potential energy, we know the sum of two is constant, and if they keep on changing in each other. So here at a distance, when the alpha particle started, they were having full velocity, full kinetic energy, and that has converted to potential energy here. So I want to calculate kinetic energy, but I have no data for that. Can I calculate potential energy here and say that that is the value of kinetic energy at this point? Yes, that is how we are doing it in physics. At any place, count the sum of the two. A ball which is dropped will have maximum kinetic energy just before touching the ground. At the top, velocity is 0. The full energy is in the form of potential energy. When it gets dropped, here the velocity is maximum. The full potential energy is converted into kinetic energy. So I can calculate this kinetic energy with the formula of mgh, because that is the one which is converted here. So the same thing is here. So I want to find out what is potential energy here, because that will be kinetic energy here, and with that I will do certain calculations. Okay. Now this particle, this is coming from a source which is radioactive source, and from there when it comes out, I have means to calculate its kinetic energy when it comes out from there. So I already know how much is the kinetic energy. That data is known to me. Now how we are going to use it? Please see, at any location where there is a distance r between alpha particle and nucleus, the force will be Coulomb's force, and that is 1 upon 4 pi epsilon naught q1 q2 upon r square. In this particular case, because it is alpha particle, this is 1 upon 4 pi epsilon naught. The charge of alpha particle is equal to 2e. 2e because alpha particle has got two positive charges. So its charge is 2e positive, that is measured. Okay. So this we can write as 2 into charge of electron positive multiplied by q2, that is charge on this nucleus. This has got 79 plus charge, 79 times the charge of electron. So this we can multiply with Z, that is the number, multiplied by charge, Z times E. This is to be divided by this distance. We go for this particular case, and what is this? This is distance of closest approach. So this is d square. Okay, what is the potential energy at this time? You remember the formula for potential energy, that between the two charges 1 upon 4 pi epsilon naught q1 q2 upon r. This is the potential energy formula, same as force, but the power of r is 1. So we can write potential energy at this distance, potential energy is equal to 1 upon 4 pi epsilon naught, and this is 2 z e square upon d to the power 1, because it is potential energy, not the force. So this is potential energy here. Now we have already discussed that whatever is the potential energy here, that was kinetic energy here. So this we can also write that this is equal to kinetic energy. K stands for kinetic energy. So now we have 1 upon 4 pi epsilon naught 2 z e square upon d is equal to k. Transfer d here. So we get this d minimum. We can write it here also, here also. So d minimum is equal to 1 upon 4 pi epsilon naught 2 z e square upon kinetic energy of alpha particle. Now kinetic energy of alpha particle is a known quantity to us, because when it leaves radioactive particle, at that time we measure it and we know this value. This value is known to us for alpha particles. Charge on electron is known to us. Value of Z for gold is 79, and 1 upon 4 pi epsilon naught is 9 into 10 to the power 9, that is also known to us. So we write all these values and we get it 9 into 10 to the power 9 into 2 into 79 into 1.6 10 to the power minus 19 square upon kinetic energy of the alpha particle, and that kinetic energy of the alpha particle is found to be 7.7 million electron volt. So this we write as 7.7 million electron volt. And this electron volt we will convert to joule. We know the formula how to convert it into joule. So we do all this calculation, and after doing this calculation we find that d minimum, it comes to 3 into 10 to the power minus 14. Okay, this. Or if you want to remember a general formula, then you leave this z, then this will be 3.84 into 10 to the power minus 6 multiplied by this z. So this gives the formula for distance of closest approach for any material which has got atomic number Z. Now we have used gold, so we will put Z equal to 79. So for gold Z is equal to 79, and this D comes to be 3 into 10 to the power minus 14. Now 10 to the power minus 15, we give it the name Fermi. So this we can write as 30 Fermi, femtometer or Fermi. So 30 femtometer is the closest approach of alpha particles for gold nucleus. Gold nucleus, alpha particle, this distance is 30 femtometer, and that means 30 into 10 to the power minus 15 meter. Now With this, we can find the idea that what should be the size of this. Yes, it is very clear. This size has to be in the order of 10 to the power minus 15, right? Because if it is larger than that, then it would have written from here 10 to the power minus 14, from 10 to the power minus 13, but it has penetrated and it has gone to the distance which is 10 to the power minus 15. So, the size should be 10 to the power minus 15, whatever is the number. Later, with other advanced experiments, we could find out the size of gold nucleus, and we found that it is actual size 6 FM, 6 femtometer, and you see this is within 30. So, this was 30, naturally this will be 6. So, this experiment helped us, the closest approach calculation helped us to find out the parameters of its size, that it has to be so small. Now, once we calculate that size of the nucleus is to the order of 10 to the power minus 15, and we know that size of the atom is 10 to the power minus 10. There is a gap of 10 to the power 4. How we explain that? It is an empty place, and in that empty place there are electron clouds. Electrons are moving in the orbit. That is what Rutherford said. So, this calculation helped us to find out size of the nucleus. Now, in the other chapters, we will study what are the energy levels of the different electrons which are moving around the nucleus and how the shape was calculated. Thank you.